Today we are breaking down OneVision-Encoder, Codec-Aligned Sparsity, as a foundational principle for multimodal intelligence. It's from the researchers at Glint Lab, AM for Health Lab, and MVP Lab.
And this paper, it hits hard right out of the gate with a massive premise.
Which is?
That AGI is fundamentally a compression problem.
Yeah.
The authors argue that our current vision transformers, VOTs, are just wildly inefficient.
How so?
They process these dense pixel grids uniformly. They completely ignore the fact that visual signals, especially video, are just incredibly redundant.
So their solution is to align the deep learning architecture with video codec principles, like HEVC.
Exactly.
And they've built a model that focuses compute solely on surprise. So the predictive residuals that actually define motion and meaning, it just ignores the static background.
And the results are, well, they're serious. By focusing on just the top 3.1% to 25% of regions rich in signal entropy, OneVision-Encoder outperforms these massive backbones like Qwen3-ViT and SigLIP2 across 16 benchmarks.
What's the key stat?
A huge 17.1% top one accuracy improvement on diving 48. And it does this while using significantly fewer tokens.
That is a massive efficiency gain. Okay, let's get into the architecture.
Let's do it.
So, to really get why this paper is such a big deal, we should probably look at the current state of video modeling. We're talking models like MAE, VJPBA, CLIP. How do they usually handle video?
Well, the standard approach is what we call the dense grid method. You take a video, you chop it into a sequence of frames, and then you chop each frame into a grid of patches.
Okay.
Then you feed every single one of those patches into the transformer. It treats video as a massive uniform brick of data.
Which sounds thorough, right? I mean, you don't want to miss anything.
It is thorough, but it's also incredibly naive from an information theory perspective. I mean, think about a security camera pointed at a hallway. For 60 frames, that's just 1 second of video. The walls, the floor, the ceiling, they don't change.
Right.
But a standard vision transformer processes that static wall 60 separate times. It treats it as new information every single millisecond.
So we're burning massive amounts of GPU compute just to rediscover that the wall is, in fact, still a wall.
Exactly. It's analyzing redundancy instead of signal. And this connects directly to that hook we mentioned earlier, the Sutskever hypothesis.
Right, that's referencing Ilya Sutskever's 2023 claim that intelligence is compression.
And the paper takes that idea literally. If intelligence is compression, then your neural architecture needs to resonate with the structure of the data it's compressing. And video data isn't dense, it's sparse.
Okay.
The actual information, the surprise, like a person walking into that hallway, is rare and it's localized.
So instead of reinventing the wheel, the authors looked at technology that solved this exact problem decades ago.
Video codecs.
Things like H.264 or ATVC.
Exactly. If you actually look at how an .mp4 file is stored on your hard drive, it is not saving 60 full images per second. That would be wildly inefficient. It uses a system of iframes and pframes.
Let's break that down for anyone who isn't a video engineer. Iframes are intra-coded, right?
Yeah, think of an iframe as a complete high-res photograph. It establishes the context, the scene, the background, the lighting. It's the data-heavy part.
Okay.
But then for the next sequence of frames, the codec uses pframes, or predicted frames.
And these pframes don't contain the whole picture.
No, not at all. They are essentially sparse instructions. They contain motion vectors and residuals. A motion vector might just say, take this block of pixels from the last frame and move it 10 pixels to the right.
So if a car is driving across the screen, the p-frame just tells the player to move the car shape. It kind of copies the road and the sky from the previous iframe.
Precisely. And the residual is just the error correction, the tiny differences where the prediction wasn't quite perfect. The paper's whole point is that visual understanding should work the exact same way.
Right.
Why are our AI models reanalyzing the static road in the sky when they should be focusing entirely on the sparse, localized evidence of the moving car?
Conceptually, I'm completely sold. It makes perfect sense.
Mm-hmm.
But implementing that into a transformer sounds like a nightmare. Transformers love order. They like dense tensors and regular grids.
Mm.
If you start just deleting patches because they didn't change, you break that whole grid structure. So how did they actually build this OneVision-Encoder?
They introduce a mechanism they call Codec Patchification. It's basically a direct translation of that HEVC logic right into the tokenization layer of the model.
So instead of uniform sampling, just taking every square in the grid, they're dynamically selecting specific ones.
Yes. They look at the video bit stream itself. They take those motion vectors and the residual energy, which is basically the mathematical measure of how much change is happening here, and they calculate a saliency score for every single patch.
Okay, so walk me through the sequence. What does the model actually see?
It starts with an iframe. The model processes that fully. It needs to know what the hallway looks like to establish the scene. But for all the subsequent p-frames, it just applies a mask based on that saliency score.
And how aggressive is this filtering? Are we talking about dropping, like, half the tokens?
Much more than that. They select a fixed proportion, somewhere between 3.1% and 25%, depending on the configuration.
Wait, 3.1%? They're throwing away nearly 97% of the visual tokens in the predicted frames.
And yet they argue they aren't losing information, they're just throwing away the redundancy. This leads to an 87.5% token reduction compared to dense processing.
Let's put that in the context of a token budget, because that's really what limits context windows in these models.
Right, so imagine you have a budget of 2048 tokens. In a normal dense model, that might get you, what, maybe 8 frames of video? That's barely a split second.
Not much at all.
With this codec sparsity, OneVision-Encoder can represent 64 frames over 2 seconds of action with the exact same token budget.
That is a massive efficiency gain. You're effectively compressing the timeline right into the context window. But I see a techno problem here. If you're dropping patches based on motion, you create what the paper calls an irregular layout. If I just give the model a bag of tokens, one from frame 10, top left, and another from frame 15, bottom right, how on earth does the model know where anything is or when it happened? You've completely destroyed the grid.
That is the million-dollar question. If you lose the grid, you lose the implicit position. Standard transformers rely on that grid to know that pixel A is next to pixel B. So they solved this with a custom positional embedding called 3D rotary position embedding.
Or 3D rope. Rope is pretty standard in LLMs now, but usually it's 1D for text sequences. This is 3D.
Correct. Standard ROPE handles a sequence of words. This has to handle space and time relative to each other. They use a dense video codec rope, which encodes spatiotemporal offset.
Break that down for me. Offsets implies it's measuring the distance between the tokens.
Exactly. It doesn't just say this is at coordinate XY. It calculates tie TJ for the time difference to the x-axis and the x-axis and rho J for the axis.
So it's explicitly telling the model, this token is 3 frames later and 20 pixels to the right of that other token.
Yes. So even if there is this huge gap of empty space between them because the background was deleted as redundant, the model knows exactly how far apart they are in 3D space.
Wow.
It allows the model to maintain a perfect mental map, a 4D structure of the video, even though it's only seeing a few scattered patches per frame. It effectively stitches the sparse data back together in the model's mind.
That is really clever. It completely decouples the information from the grid format.
And it's flexible. They also have chunk-wise and spatial rope-E variants, which means this same model can handle single images, which are just dense iframes, or these long codec sparse streams with one unified embedding scheme.
So it doesn't break when you switch from a static photo to a movie.
Not at all.
Okay, so we have the architecture. Only look at the moving bits and use some clever 3D math to keep track of where they are. But a brain needs more than just eyes. It needs to know what it's looking at. The paper mentions that just using sparsity isn't enough. You need a better training objective.
Right, and this is where they take a swing at contrastive learning, specifically methods like CLIP, which is, the industry standard right now.
Right. CLIP trains by verifying images against text captions. You showed a picture of a dog and the text, a dog, and it learns to match them. Simple enough.
It works, but the authors argue it has a fatal flaw for video. CLIP relies entirely on external language supervision. If your caption says, "a dog runs," that's great. But does the caption describe the physics of the paws hitting the ground?
No.
Or the sway of the grass or the lighting change?
No. Language is sparse. Visual reality is dense. A picture is worth 1,000 words, but we usually only train it with, 10 of them.
Exactly. So if you only train on text, you miss the fine-grained visual details, the physics of motion. So OneVision-Encoder uses a cluster discrimination objective instead.
Cluster discrimination. How does that differ from just matching text?
Well, instead of just pairing an image with a sentence, they use what they call a concept bank. They performed offline clustering on a massive data set of images and videos to create over 1 million semantic concepts.
1 million. So these aren't just generic labels like dog or cat.
No, these are ultra-specific. They have object-level semantics from images and motion-level semantics from videos. The training objective is to force the model's embeddings to pull closer to these semantic centroids, the center of that concept class.
I see. So rather than just trying to match a specific text string, it's trying to map the video to a geometric point in meaning space that represents, I don't know, diver rotation mechanics or water splash patterns.
Precisely. This forces the model to learn structure-object permanence and motion dynamics without needing a perfect text description for every single frame. It's learning the visual consistency of the world, not just the linguistic description of it.
Okay, so we have an efficient, sparse architecture and a robust, concept-heavy training method. But usually when we talk about efficiency in AI, there's a tax. You trade accuracy for speed, you use a smaller model, you get dumber results.
That's the conventional wisdom. But the core finding of this paper, and this is why we're talking about it, is that efficiency and accuracy are positively correlated here.
It actually gets smarter by ignoring the data.
By ignoring the noise, yes. Let's look at the comparisons. They pitted OneVision-Encoder against the heavy hitters, SigLIP2 and Qwen3-ViT.
And these are massive state-of-the-art models.
Huge. So they ran a multimodal evaluation, plugging these vision encoders into a Qwen3-4B language model. They tested it on 16 benchmarks: video, image, document understanding. The result: OneVision-Encoder consistently outperformed SigLIP2. But the real shocker is the comparison with Qwen3-ViT. This is a classic David versus Goliath situation.
And give me the tail of the tape.
The Qwen3-ViT model was pre-trained on over 2.1 trillion tokens of data. I mean, that is an ocean of information. OneVision-Encoder, it saw roughly 100 billion caption tokens.
That's what, a 20th of the data?
Roughly 20 times less data, and yet OneVision-Encoder wins. On video understanding tasks specifically, it achieves an average improvement of 4.1% over Qwen3-ViT.
That is incredibly validating for that whole quality over quantity argument.
Yeah.
If you filter out the noise before the model even sees it, it just learns faster.
Exactly. And to prove it's not just about language alignment, they did attentive probing. This tests the raw representation quality without the language model helping out.
And this is where that diving 48 stat you mentioned at the top comes in.
Yes. Diving 48 is a notoriously hard benchmark because it's purely about motion. You can't solve it by just spotting a diving board or a pool. Those are in every single video in the dataset.
Right.
You have to distinguish between a forward pike and a reverse tuck. The background is identical, only the motion differs.
And OneVision-Encoder crushed it.
A 17.1% top one accuracy improvement over SigLIP2, and an 8.1% improvement over Dino v3.
17% is huge in this field. Usually, researchers are fighting for 1 or 2% increments.
It proves that the model isn't just recognizing static objects. It's truly understanding the complex flow of motion because it's explicitly being fed the motion residuals from the codec. It's seeing the dive, not the pool.
I want to play devil's advocate for a second, though.
Go for it.
You mentioned it uses the motion vectors from the video file to pick which patches to look at. Could it be that just any sparsity works? Maybe transformers just like having less data to crunch so they hallucinate less, or maybe the performance boosts just because it's a transformer and we're overthinking the whole codec part?
That is a very healthy skepticism, and the authors actually anticipated exactly that question. They ran what I think is the most interesting part of the paper, the sanity check or ablation studies. They call them counterfactual interventions.
Counterfactual intervention sounds like a sci-fi trope. What did they actually do?
Okay, experiment 1. They took the same video, but instead of letting the codec pick the motion patches, they forced the model to look at random non-motion patches.
So forcing it to look at the static wall instead of the moving person.
Right. Same number of patches, same video, same sparsity ratio, and the performance dropped significantly.
Okay, so that tells us the location of the patch matters. You can't just pick random spots to save compute.
Correct. But then there's the question you asked. Maybe it just needs to see movement. Any movement.
Right.
That was experiment 2, and it's the kicker. They replaced the patches with motion patches.
Motion energy, like there is movement at coordinate XY, but the pixels were from a completely different clip.
Exactly. They preserved the where of the motion, but completely broke the what. The performance was even worse.
So it's not just pay attention to movement. It's pay attention to this specific movement and how it relates to the context of this specific scene.
Correct. And then finally, they did a patch position shuffle where they kept the right patches but just scrambled their locations in the grid. Performance collapsed there too.
So that confirms it. The model is actually relying on this specific semantic content of the motion residuals. It's not a statistical artifact. It's reading the story of the movement.
It effectively proves the hypothesis. Intelligence, at least in this context, really is about compressing the predictive structure of the world.
I would love to know what this actually looks like under the hood. The paper has some visualizations, figure 5 specifically. Can you paint a picture for us? If I could see through the model's eyes, what would I see?
Yeah, it's fascinating. Imagine a sequence of a diver jumping off a platform. You have the first frame, the I-frame. In the visualization, every patch is active. It just looks like a normal photo.
Establishing context, it needs the baseline.
Right. But then you move to the P-frames, the next few seconds of the dive. The visualization uses a heat map. Cool colors like blue mean ignored, and warm colors like red and yellow mean processed.
Okay.
In the P-frames, the background, the stadium seats, the tiles on the wall turns deep blue. It's effectively invisible to the compute. But the diver is glowing red and yellow.
Like a thermal camera tracking them.
Exactly. And not just the diver. In another example with pedestrians, the people walking are lit up in warm colors, but the sidewalk they're walking on is cold and blue. It visually confirms that the saliency score from the codec is acting as a natural, pre-computed attention mechanism. It automatically knows what matters.
It's almost like the model has evolved a fovea. You know how our eyes only have high resolution in the very center? This model is ignoring the periphery and just focusing on the action.
That's a great analogy, and it does it by leveraging the data structure that was already there in the file format. It's a biomimicry via digital compression.
So let's zoom out. What does this mean for the field? We have a model that aligns with video codecs, saves massive amounts of compute, and understands motion better than models trained on 20 times the data.
I think the takeaway is a shift in perspective. For a long time, we've treated video as a stack of images. We just threw more and more compute at the stack. This paper suggests we should view video as a flow of predictive information.
We stop asking what is in this frame and start asking what changed.
Exactly. And I mean, think about the applications. If you can process video with 87% fewer tokens, you bring high-level video understanding to edge devices. Drones, robots, smart glasses, things that can't carry a massive GPU rack with them.
That's a game changer for robotics. Real-time understanding without the lag.
But even beyond that, there's the philosophical angle.
What's the provocative thought to leave us with today?
Well, if we accept Sutskever's idea that AGI is a compression problem, we need to look at our tools. Right now, we build AI architectures that process data, but maybe our architectures should emulate the compression algorithms we use to store that data.
Go on.
We use codecs like HEVC because they are mathematically efficient descriptions of reality. They strip away the noise and they keep the signal. If a neural network is trying to model the world, maybe the most efficient path isn't to brute force the pixels, but to adopt the logic of the codec itself.
So Codec-Aligned Sparsity might not just be an optimization trick.
It might be the engine for the next generation of visual generalists.
That is a fascinating thought. Maybe the secret to AGI has been hiding in our .mp4 files all along.
It just might be.
Thank you so much for tuning into this update on AI research. We'll be back with another stack of papers soon.
Goodbye, everyone.
See you next time.